All right, in this video, we're going to go through the sequential definition of continuity, which is going to be what we take as the definition of continuity at a point. And then we'll talk about the epsilon-delta version and show that they're equivalent. And then we'll go from there. So let me just state the definition of continuity at a point, the sequential definition. So here we go. So definition. So let f be a real valued function with the domain of f. So this is the notation that the book uses and the notation we're going to use to represent the domain of a function. So the domain of f is a subset of the real numbers, and so we say f is continuous at x naught if for any sequence xn of points in the domain of f such that xn converges to x naught, we have that the limit of f of xn is f of x naught. Okay? So that's the definition of continuity at the point x naught, right? Then if f is continuous at every point in some subset S, we say f is continuous on S, and if f is continuous on its entire domain, we just say f is continuous. So calling a function continuous is sort of the strongest thing you can say. Some functions might be continuous at some points in their domain and not others. And those functions would be called discontinuous, but they might be continuous at some points. So saying a function is discontinuous or saying a function is not continuous does not imply that it's discontinuous at every single point. It only implies that there exists at least one discontinuity somewhere in the domain. Okay? So that's the definition. We call this the sequential definition because it's phrased entirely in terms of sequences, right? We quantify all sequences of points in the domain which approach the given point x naught, and then we make the definition in terms of the behavior of this corresponding sequence f of xn, right? So it's like if you just pick a sequence xn that converges to x naught and look at what happens to the sequence f of xn, you know, if this converges to x naught, then f of xn better converge to f of x naught. If there's even one sequence xn approaching x naught such that this does not hold, then the function is not continuous at x naught. Okay, so it's another situation where it's very important to keep track of the for all and there exists quantifiers. And remember that if you negate something that's said to be true for all values of a particular parameter, then the negation is saying that there exists some value of that parameter for which the property is violated, right? Okay, so that's the sort of straightforward definition. Actually, before we even go any further, I'd like to pose a lecture question here. So this is lecture 11, question 1. Okay. So suppose f is a function, is a real valued, obviously. And the domain of f is the set of natural numbers. And say f of n is, 1 if n is odd, or 0 if n is even, right? So again, I mean, it's sort of, it is sort of a, you can think about f as a sequence. It has the same data as a sequence, but it's actually a function. Right now we're considering it as a function whose domain just happens to be the set of natural numbers, okay? So, so let's say that this is our function f, then is f continuous at x equals 3, let's say, or any point really. I mean, obviously it seems like the answer should probably be the same for all of them, but you can pick whatever point you want and sort of ask this question. Okay, so think about it, try to go back to the definition and see if you can apply the definition here to determine whether this function is continuous at a given point. And when you unpause, I will answer. And remember to include this on your homework. Okay, so the answer here is actually yes. And I think this might be a little bit surprising for some people, because if you look at the graph, right, I mean, it's just a bunch of dots, right? So it's sort of like, how can you call that continuous? I mean, it's, it's all disconnected. I mean, where's the curve, right? I mean, you can't draw the graph. You have to, like, lift your pencil or whatever if you're drawing this graph. It's just a bunch of dots, right? But this is sort of a subtlety of the definition, okay? If we go back here, it says f is continuous if for any sequence of points in the domain of f such that the sequence converges to x naught, right? In the domain, the key being in the domain, right? Any sequence in the domain which converges to x naught, then we have some statement, okay? That has to be true. So the question is that statement violated for any sequence in the domain which approaches x equals 3, right? The domain is the natural numbers. So let's just think about what are the sequences xn in n which approach 3. Well, anything which is eventually constant, right? If the values xn are only allowed to be positive integers, then the only way this sequence can actually converge to 3 is if eventually, after some point, it's just always equal to 3, right? Xn has to be 3 for every value of n past a certain capital N. Because if it's not, if it keeps jumping to other values, then that means that, there will be places where xn minus 3 absolute value is going to be at least 1, and that will happen like infinitely many times, and that's not allowed, right? So eventually xn just has to equal 3 forever, and if that's true, then f of xn equals 3 for, n greater than some capital N, right? So f of xn also converges to 3, right? So if xn converges to 3, then xn has to be eventually constant, and that means f of xn is also eventually constant. So f of xn, or sorry, it doesn't converge to 3, it converges to 1, sorry. So f of xn equals 1 for, okay. And that's what we wanted, okay? That means that f is continuous. So f is continuous. And this is like just a weird thing about the definition. And the reason for it, really, this happens anytime there's a point in the domain where the point is like isolated from all the other points in the domain. So if a point in the domain of f is isolated from all other points in the domain, then it's automatically continuous at that point, no matter what. So actually, literally you could assign any sequence of values to f of n. You could make f of n have any values for each, like whatever value you want for every value of n. You could just pick a random value, and f would still be considered to be continuous, just because every point in its domain is just isolated from all the other points, meaning you can draw an open interval around any point in the domain where there are no other points in the domain in that interval, okay? Another way of saying that is that the domain of f is basically a discrete set in the real numbers, or rather that as a subspace, as a topological subspace of R, or as a subspace, as a metric space in R as a subspace, it has a discrete topology on it. But you don't have to worry too much about that. Just for those of you who are interested in topology. So anyway, right. It's very important to really pay attention to this, like in the domain, and try to get used to it, because it'll keep popping up in like all the proofs we do about continuity. Like if there's ever any, like, if it's ever not clear exactly what the domain of f is, we'll have to account for situations where like the domain of f might look pretty weird, okay? So anyway, yeah, that's it for that. All right, so now let's look at Theorem 17.2, which is basically stating that the definition we just gave, the sequential definition, is equivalent to the other definition that we kind of sort of gave in the first part, which is the epsilon-delta definition, otherwise known as the epsilon-delta property of continuous functions. So let me state the theorem. So 17.2, this is the epsilon-delta property. So let f be a real valued function with domain of f is a subset of R, then f is continuous at x naught in the domain, sorry, if and only if, and then we state this. So for all epsilon greater than 0, there exists a delta greater than 0 such that for all x in the domain of f with x minus x naught less than delta, we have absolute value of f of x minus f of x naught less than epsilon, okay? So this is almost identical to the statement that I made in the previous video, just with this extra thing of x being in the domain of f, right? And again, it's just those are the only values of x we're concerned about, because obviously you can't say anything about values of f at points that are not in the domain of f, because it has no values at points not in its own domain by definition, right? So you just have to impose this requirement on x that are in the domain of f within distance delta from x naught. So if you go back here, if you look at like this example in the lecture question, what this is saying is basically like you can find some delta around, x equals 3, so that all of the points in the domain of f near, like within delta from x equals 3, have their values being within epsilon away from, you know, f of 3, which is 1. But if you think about it, if you choose delta small enough, there just are no other points in the domain of f that are within delta. Like if delta is 1/2 or something, there are no points in the domain of f that are within a half away from x equals 3, right? I mean, that's just because the only points in the domain are integers. So they're all at least 1 away. So with delta equals 1/2, there's only one point in here, which is just x equals 3 itself. That's the only point in the domain within this open interval. And so clearly, of course, for that value of x, f of x is within epsilon from f of x naught because they're the same number. It's just 3, right? So that's kind of why this can look a little bit weird sometimes. If the domain of f itself has a funny shape, you get strange stuff, kind of. But anyway, so that's the epsilon delta property. So they symbolize this. I mean, in the book, they call this 1. In their proofs, I don't know. I'm just going to call it. This is what I call the epsilon delta property. So you'd say that, you know, you could say that f has the epsilon delta property at x naught. But of course, because it ends up being equivalent to being continuous at x naught, you know, you can just use continuity interchangeably to mean, you know, continuity according to the sequential definition or continuity according to the epsilon delta definition, right? So anyway, let's sort of think about the proof here. In fact, I'm going to take a minute or two to draw a little sketch. So, okay, so this is an if and only if type statement. So there are sort of two directions to go, all right? And the sort of forward direction, I guess, if you want to think about it that way, is, well, actually, I guess it's not really the forward direction. But one of the directions is somewhat easier. So if you assume the epsilon delta property is true, then it's somewhat straightforward to show that our sequential definition of continuity has to hold. So let's take that first. So suppose the epsilon delta property holds at x naught, right? So here's what I'm going to say. Okay, so let's show and suppose, so we want to show for all xn converging to x naught, we have f of xn. So this is for all sequences xn in the domain of f, of course. F of xn approaches f of x naught. Okay. In other words, so let's let xn be a sequence in the domain of f such that xn approaches x naught. Okay. Now we want to show that f of xn approaches f of x naught, right? So here's what we have to work with. We have the epsilon delta property, and we have that xn converges to x naught, which is, of course, vital, right? And I'm just going to sort of state these things in words. So xn approaching x naught is the same thing as saying we can make xn close to x naught. Okay, that's, I guess, by making n large, right? The epsilon delta property is the same thing as saying we can make f of x close to f of x naught by making x close to x naught, right? So just think about these two statements, right? We just have to combine them, basically. This lets us make xn close to x naught. This lets us make f of x close to f of x naught whenever x is close to x naught. So then we can make f of xn be close to f of x naught just by making xn be close to x naught and invoking this property, right? So let me just make that a little bit more formal now. So of course, in the end, we want to make f of xn close to f of x naught, right? So we want to make them be within epsilon from each other, where we let epsilon be, some arbitrary positive constant. So let's let epsilon be greater than 0, right? We want to show the existence of capital N. But first, what we do is we get a delta, right? So here you can see I've drawn a picture of the epsilon-delta property. So this is, epsilon, and then of course this is delta, right? So we let epsilon be greater than 0. Then we'll use the epsilon-delta property first to pick a delta. So that way we know like what we're aiming for, right? We have to make, the question is like, we have to make xn be close to x naught, but the question is how close do we have to make it, right? Well, the epsilon-delta property kind of gives us a way of getting a handle on that, because delta is exactly, how close we have to make x be to x naught, right? So then there exists a delta such that f of x minus f of x naught is less than epsilon, whenever x minus x naught is less than delta, and x is in the domain of f, of course, right? Okay, so now we have our delta. That's basically our target of how close we have to get to x naught. So then we just have to use the fact that xn converges to x naught to make it be within delta from x naught, right? So then there exists a capital N such that for n greater than capital N, xn minus x naught is less than delta, right? But then, we just have f of xn minus f of x naught is less than epsilon, right? So what happened is now we have our sequence, right? This is xn, and it's approaching x naught, and eventually it gets inside of this band, right? But that means that all of the f of xn's get inside of this green band, but then that means they also have to stay inside the red band because, that's how we chose delta, right? So for n greater than this capital N, you don't have to do anything else. This is actually the capital N that works. So f of xn converges to f of x naught. Okay, so that's one direction. That shows that if the epsilon delta property holds, then the sequential definition holds. So now let's consider going the other way. So I'm gonna take a couple seconds to erase here. Okay, so now let's suppose that the epsilon delta property fails at x naught, right? So that's a little bit complicated, but remember, the whole reasoning here is that if we show that this means, so what we want to do, right, is show that that there exists a sequence xn converging to x naught such that f of xn does not converge to f of x naught, right? That's what we want to do. We want to violate the definition of continuity, because then that's basically we'll be proving by contrapositive that if the sequential definition of continuity holds at x naught, then the epsilon delta property also holds, okay? So by showing that if this fails, then this one fails, we're doing a proof. It's basically proof by contraposition. If you want to think about it as contradiction, that's also okay. So this gets a little bit complicated to think about just because you have to be really careful about how you negate these statements, right? So if we say the epsilon delta property fails, okay? So if we're saying that the epsilon delta property fails, that means that there exists some epsilon, right? Such that, some epsilon greater than 0, such that there is basically, in words, there is no choice of delta which will force f of x to stay within epsilon from f of x naught, right? There exists one value, at least one value of epsilon. There is at least one value of epsilon such that there is no choice of delta, which forces f of x to stay within epsilon of f of x naught for all of those values. So basically what that means is for all deltas, right? Because we're saying there's no good choice of delta. So in other words, every choice of delta is bad, right? For all deltas greater than 0, now we want to say that delta does not work, right? That delta is a bad choice of delta. And what does that mean? That means that not all of the values of f of x are within epsilon, right, away from f of x naught, for that are with, you know, not all values of f of x when x is within that delta, right? So there exists some value of x in the domain of f with the absolute value of x minus x naught less than delta, such that the absolute value of f of x minus f of x naught is greater than epsilon, right? This is what it means to say that our choice of delta didn't work. There's at least one value of x within that delta where f of x breaks the bound, basically. Oh, it's too far away. Where f of x is too far away from f of x naught. There's at least one choice of x that is within this radius for which this is true, right? Okay, so now we just have to leverage this. Remember, it's like when you negate stuff, you just flip all of the for alls and there exists, and then you like negate whatever the statement at the end was. So it's like the for all epsilon became a there exists epsilon. The there exists delta became a for all delta. Then for all x with this condition became there exists an x with this condition, and then f of x minus f of x naught greater or less than became, I guess, greater than or equal to. It doesn't really matter. Okay, greater than or equal to. Okay, so this is our negation here. So now what we can do is, okay, you know, pick this epsilon, right? So pick this epsilon and consider delta equals 1 over n, right, for each value of n. Okay, so we're considering it sort of a decreasing sequence of deltas, right? And then for each of those deltas, what we're going to do is make xn be the bad point, like a point where f of x is too far away for that delta, right? So take xn such that f of xn minus f of x naught. So this xn is in the domain of f with absolute value of xn minus x naught less than 1 over n, right? We're taking delta equals 1 over n. So we can pick within the radius 1 over n, we can pick a value xn such that this is greater than or equal to epsilon. That's exactly what this is saying over here. Okay, so we're basically picking these points, you know, getting closer and closer to x naught, but the values keep staying outside of this band, right? So then clearly xn converges to x naught, but f of xn does not converge to f of x naught. Okay, sorry for the cramped writing here, but I hope you see what I'm saying, that, you know, by sort of stating the negation here correctly, we just chose a sequence such that, you know, that's what we wanted to do. We wanted to show this sequence existed converging to x naught such that f of xn does not converge to f of x naught. And that's exactly what we did, because we were able to force f of xn to be at least epsilon away for every value of xn, even though xn is getting closer and closer to x naught, right? Xn is within 1 over n from x naught. So clearly it converges to x naught. But these do not ever get closer than epsilon. So that's a problem, okay? So that basically shows that if the epsilon delta property fails, then the function is not continuous, which means in turn that if the function is continuous, the epsilon delta property must hold. So they're equivalent, okay? So the moral is our definition of continuity is equivalent to the epsilon delta property. Okay, so from this point on, you can basically treat them as, if you assume that a function is continuous, you can just use whichever version of the definition you want, and it'll be fine. Although ideally you would maybe at least early on make sure to cite the theorem or something like that. But eventually that won't really be a problem. We can take for granted that they'll be equivalent. All right. Anyway, so in the next video, I'll look at some examples of applying the definitions here to either show that a function is or isn't continuous, kind of like we did with sequences, and then we'll do some of the theorems about what operations you can do with continuous functions, much like we did for sequences as well.